Okay, so this is, as I was saying last time, the theory of plate tectonics is really a relatively new theory. Okay, it just started kind of initiated in the 1960s, and then later on it became more common, and it's really what we call a unifying theory today. We base a lot of our understanding on. So if we have a plate around a sphere, okay, if we have this sphere that's moving around these plates, these little kind of rigid plates on the outside of a sphere, they can really only move in three different ways. You could either have them move side by side from one another, right? Okay, side by side. And that would be what we call a transform boundary. Okay. You could either, that would be this guy right up here. Okay, let me turn my laser pointer on here. Okay. This guy right up here. And then you'd have, at that location, you'd have earthquakes, but you wouldn't have any volcanics. And the reason is because you don't have any magma or any way that the magma is generated. Because you have to remember the way the magma is generated. You either have to have added heat, you have to have decompression, or you have to have added volatiles. In a transform plate boundary, you have none of those, really. Okay, so you don't technically get volcanics, but you do have lots of earthquakes. A great example of one of those is the San Andreas Fault in California. Okay, so another one might be one like this. Well, so instead of it actually moving past one another, they might be moving towards one another. Okay, so here's the sphere moving towards one another. That would be converging. Okay, so con meaning with and converge together. So it's coming together in a sense. Okay, now in this case, you have two plates, and one plate here, the oceanic plate, is denser. It's made of mafic materials, remember, so mafic materials are denser, and continental materials are less dense. So the mafic material will go down beneath the felsic material, right? And so when it goes down, though, it brings water with it. So the pressure actually increases, not decreases. So that's not a cause of melting. But as it goes down, the heat increases. So that's one way magma can be generated. But also you're adding water from that wet oceanic plate down into the mantle, therefore causing the mantle to melt. And therefore, as the mantle melts, the magma will rise because it's less dense, forming a volcano on the interior portion of the crust. And because you have a felsic crust and a mafic bottom, you end up with an intermediate or more felsic magma to form these big, dangerous volcanoes, right? We'll show that more in a second. Now the last one here is your divergent plate boundaries. So if you have them coming together, convergent, sliding past one another, okay, that's transform. And the last one here is your divergent, where they're going apart, right? Okay, so if you have magma down below with added heat and it's rising, what's happening to pressure? Pressure is going down. It's decompressing, which means that it can actually turn into a magma, right? Okay, and therefore it will melt, pushing up on the crust, causing the crust to actually rise because it's more buoyant, and therefore then break apart and push apart the actual ocean floor. Okay, we'll talk about how that actually all occurs, but it's through a process that we call convection that initiates it, and then we have other processes that continue it on, and we'll talk about that in a little bit. But this is a divergent boundary. Diverge, or to go away from another. Okay, like disagreement, it means that you agree. Dis is the away from each other, so you agree, and so it's a separation. Okay, whereas converge is to come together. To converge is to come together with, and so that's those ideas. The root words are, by the way, the root words of different roots of some words will tell you a lot about what's going on there. Okay, so at a convergent boundary, compressional force, you're pushing together. Okay, divergent, extensional force, where you're extending things apart, and then transform, which is a transitional force where you're sliding past one another. So I have an example of this. These are some blocks that I cut out, and you have these blocks here. Let me see if I can move back and show it to you better. So if I push together, it's compressing. If I pull out, it's extending. And if I have them go side to side, it's this translational movement, right? Okay? And we'll come back to those later to give you an understanding of that better. Okay? So there's lots of evidence. There's lots of things to look at to help us to understand the clues to if this is working or not. one of the best is what we call the geochronology of the ocean floor. This is a map that actually is a fairly cool map. It's a map that shows the age of the seafloor around the world. What they did is they went around and drilled boreholes into the rock, or basalt. If you remember that, that's a mafic rock, and the oceanic crust is more dense, therefore mafic material mostly. Okay, and we'll talk about why it's more dense a little bit later. Basically, they're drilling down and actually dating it. Okay, they're dating it through radiometric techniques and figuring out how old each of those samples are. They put those all around the world, and they start figuring out that the seafloor is youngest in the center, right where that those mid-ocean ridges are the highest, and then they get older as they go away. So it's not hard to imagine that at one point this blue over here, next to where Africa is, was once snugged right in here where North America was. And these blue portions were together at some point, right? And then it slowly goes away, the blue portions go away, the blue portions go away, and then the red portions come up. So the red portions here, what the colors actually denote here is they're denoting a certain age. The red being young and the blue being about 180 million years old. Now, we've told you this before, but the Earth is 4.5 billion years old. So why is the ocean floor only 180? Well, that's a very good question. And the question comes is that in the center here, where it's the youngest, new material is being created. But guess what? Towards the edges, over here mostly, over here, okay, they're being destroyed. One piece of the ocean floor is going down and being destroyed, and therefore it's being recycled in a sense. So at convergent boundaries, where the plates are coming together, the oceanic crust is being destroyed, and then at divergent boundaries, the oceanic crust is being formed. Okay, that's an important concept. Now, something that's also noticed here, that this distance here is kind of thin, but here the distance is really thick. Why the difference? Well, one thing you can think about here is this distance and the time it took for these rocks to form in this red section is the same as this red section, and this kind of orange section is the same. But this one's wider, which means that this has been moving faster than this one. So around the Pacific is a much faster plate than the mid-ocean ridges here in the Atlantic. Therefore, you'll also notice that we have a lot more tectonic or earthquake activity and volcanic activity around the Pacific. We call this the Pacific Ring of Fire. And it's because we have so much more volcanic activity and tectonic activity is because of the faster moving plate that you have here. Whereas here is much slower. In reality, off our coast, this is still blue on this side, still blue on this side. We're not actually, the continental crust, the oceanic crust is not actually diving down underneath the continental crust. What's happening is here's the continental crust of North America over here, okay? And then you have the oceanic crust, and it's pushing the whole thing. Instead of it diving down, it's pushing the whole thing. Now, at some point, it might dive down. If it does, it's going to start to form volcanoes here in the eastern United States. But for now, we don't have any volcanoes. And that's a good thing if you don't like volcanoes. Okay? So we'll talk more about that a little bit later. Okay? So this next one, this map, is actually a map of what we call the topography or bathymetry. Topography is the elevation of land above sea level. And bathymetry is the elevation of land below sea level. Okay? So notice where all the mountains are. The mountains are right here along these edges. There's trends here, right? But look here, in the middle here, there's this rising, this high kind of mountain, kind of ridge in the middle of the ocean. And that's because the divergent boundary is from below is pushing up, that magma down below it is pushing up the crust to form these higher ridges. And notice as you go away from these ridges, it sinks. And why does it sink? Well, as the rock actually cools off, as it goes away from the ridge, it becomes more dense. And therefore, the whole crust sinks a little bit as it goes away. Now, why is continental crust, all this kind of blue up here, this is all continental crust, even though you have to realize all this up here, this is all still continental crust. Now you're saying, well, wait a minute, that's not part of a continent. Well, yes, it is. It is part of a continent, just sea level is higher. And therefore, because sea level is higher, it actually goes up onto the continent to form a shallow sea. However, like for example, off our coast, we have what we call a continental shelf. That is still all part of continental crust. And it doesn't actually form to transition from a continental crust to oceanic crust until you go off the continental shelf, okay, to what we call the abysmal plain down below the ocean here. Okay, so this kind of portion here is all part of continental crust. If sea level went up, that more of our continent would be submerged, and if it went down, we would have more of our continent actually exposed above sea level, right? Now notice, places where you have mountains are places where the two plates slam together. So for example, a great example of this is when India slammed into Eurasia here, okay, and therefore causing the Himalayas. Forming a big plateau behind it. It's kind of like a crumpling of one crust over another one, forming this big mountain with this high plateau behind it. So think of this as India slamming into Eurasia, pushing the other one up on top of it, forming now this big plateau that's higher elevation than over here, where India is, right? Okay, a great example of India slamming in, pushing the tall mountains, and then the plateau behind it. Okay. Other places where you have mountains are here in Africa, but this is partly because you actually have a plume from underneath pushing up. This is actually a divergent boundary. Okay, then you have mountains all along the edge of North America here, and that's because you have one plate going underneath another plate, causing it to be kind of deformed right here at the edge. But also you're having volcanics occur to form these large volcanoes. So you have volcanoes and mountains all the way up through the Andes and through North American Rockies, all the way through here, right? So they're all evidence of plate tectonics once again. This last one, this is actually suggesting earthquake occurrences all around the world. These are all earthquakes. Every single one of these dots is an earthquake that has occurred from 1990 to 1996 over a 6-year period. And that's a lot of earthquakes for over that short amount of period, right? Well, the color coding on these is how deep down below the surface the actual focus, where the actual energy releases is at, okay? So this here, it shows the earthquake locations and depths. The location of each earthquake is indicated by a small dot, and its depth is indicated by the color of the dot. The red dots indicate earthquakes that have depths between 0 and 33. The yellow and orange indicate earthquakes from depths between 33 and 70. The green is 70 to 300, and the blue is 300 to 700. Now you'll notice there are trends. Where the red is, those are shallow. They're ones that are close to the surface, and they tend to always happen in places where you have transform boundaries, where it's sliding past right there on the surface, or at divergent boundaries, where it's going up and pushing it apart. Now, it can happen at convergent boundaries, like right through here, but you'll notice when the convergent boundaries, there's a trend here. There's red, orange, green, and then blue. Red, orange, green, and blue. What's happening here is that, let me show you this here, is one of the crust plates are moving down and going underneath the other one, and as it does, it pulls apart the plate, right? Pulling apart all this portion of the plate, causing these really deep earthquakes, right? And so if you look at the red ones, they're occurred right here. Here are some of the yellow ones, and if I project it straight up, it would be orange. These ones might be the green ones, project it right up, they'll be green. These might be the blue ones, project them all up, they'll be blue. So I go back, you'll see that same trend. So you'll notice that here, you know that this plate, this is the Nazca plate, it's moving, here's the divergent plate boundary, it's moving in this direction underneath North America, causing us to have these big, what we call a volcanic arc, where volcanoes are forming, okay, along the continents here. Okay. Now this one is also a volcanic arc, but this is an island arc. And what's happening here is two oceanic crusts are coming together, forming volcanoes on the other side. Okay, so there are volcanoes on the other side to form an island arc as well. Sorry, a volcanic arc, but a volcanic island arc. Another good example of that might be Fiji, Tonga, and some of those islands out there in the Pacific, right? So these are some examples of how we can do that. You can see the actual where the plate boundaries are based off of earthquakes. And last of all, the last part of clues that can tell us about what's going on with the plates is the volcanoes. Notice they're right where you have plate boundaries as well. So all of these keys, earthquakes, volcanoes, topography, the ages of the rocks all indicate that there is